Good morning. Now we will learn about the behavior of real gases. Okay. Now real gases are those gases we have already defined. They are those gases which do not obey the ideal gas equation PV equal to nRT. Okay. Now these are a few illustrations. No need of studying all these graphs. Just understand its nature, and if you want you can have a rough sketch but of these graphs, that is how these lines, the shape of the lines will look like. No need of by hearting the values written on x and y axis. Okay, just mark the term that is given in x axis, that is pressure, and that is then in y axis pv by nrt. That is enough. Okay, no need of studying those values that are marked on that axis. It's okay. Now but it will be nice if you study this particular marking, that is 1, because this one has got a significance, because it is on this line that the behavior of an ideal gas is drawn, that is the dotted line. Okay, here also you can mark this one here with a dotted line, that is the behavior of a real ideal gas. Okay, now all these particular lines are of different gases that deviate from the ideal gas behavior that is drawn with a dotted line at the mark 1. Okay, so just draw the x and y axis, mark that terms on the x and y axis, then that one marking, draw a dotted line there and write their ideal gas, and just draw the all other gases shape, because they are all deviating from the ideal gas behavior. They are having various other intercepts other than one. Okay, that is enough. So regarding the theory, for an ideal gas, I plot of PV by nRT versus P gives a horizontal line with an intercept of 1 on the PV by nRT axis. Now real gases, however, show significant deviations from the behavior expected for an ideal gas, particularly at high pressure. Only at relatively low pressure do real gases approximate ideal gas behavior. These behaviors are shown in the figures given below. Exactly what I have told. That is, the ideal gas makes an intercept of 1 on the PV by nRT axis. See, intercept of 1 on the PV by nRT axis, and all the other gases deviate from that ideal gas behavior, and that is quite evident from these two figures given below. Now, real gas also approach ideal gas behavior more closely at high temperature and low pressure, as shown in figure. Okay, now one question is, why do real gases behave so differently from ideal gas at high pressure and low temperature? So the only condition at which a real gas behave like an ideal gas is at high temperature and low pressure. See, this condition you have to always remember, that is ideal gas real gas behave like an ideal gas at which condition? At high temperature and low pressure. Now the question is, why this ideal when the temperature goes low or when the pressure goes high, this real gas deviates from ideal gas behavior. Why? Because under these conditions, the two assumptions that we have made becomes negligible, or that is the two assumptions that we made becomes are no longer valid. Which are the assumptions? Gas molecules have negligible volume and the intermolecular interactions are negligible. That is, these two assumptions that we make become invalid at high pressure and low temperature. That is why the real gas deviates from ideal gas behavior. So a real gas behave like an ideal gas only at high temperature and low pressure. Now this graph actually shows the effect of temperature on the behavior of real gases. So as I said before, just mark the x and y axis and draw that intercept marking 1 there and write their ideal gas and show various other gases. They are all deviating from the ideal gas behavior. That is, they are all making intercepts other than 1, right? Okay. This example is shown for a nitrogen gas at different temperatures. Now, because molecules of an ideal gas are assumed to have zero volume, ideal gas molecules are supposed to have zero volume. In that case, volume available for their motion will be the same as the volume of the container. Whereas molecules of a real gas have small but measurable volume, that is, their volume is not negligible. As a result, at low temperature, the gaseous molecules are far apart. But as pressure of gas increases, the intermolecular distance becomes smaller and smaller. See, it is very clear from the figure given below. That is, as pressure, this is at low pressure, so all the molecules are far apart. There is a large distance between the molecules. But when the pressure becomes high, what happens? All the molecules have come close together. That is, the molecules are close to each other. In such cases, volume occupied by the gas molecules will become significant. That is, they are of importance. It cannot be neglected when compared with volume of container. So volume occupied by gas molecules will be greater than the volume predicted by ideal gas law. Thus, at very high pressure, the measured value of PV by nRT will be greater than the value predicted by ideal gas law. So it is nothing but we can say that uh, ideal gas molecules, its volume is considered to be 0. So volume occupied by ideal gas molecule will be the same as the volume of container. But in the case of real gas, volume of gas molecules is not negligible. Instead, uh, the, it is comparable to the volume of container. So when pressure is low, molecules are far apart. When pressure is high, intermolecular separation between the molecule decreases. That is, molecules will come close together, and hence the volume occupied by them will be comparable to the volume of the container. This is quite clear from these two figures, and it is once again written here. That is, at low pressure, volume occupied by molecules is small compared to volume of container, whereas at high pressure, volume occupied by the molecules is comparable to the volume of container. See this one. This is once again explained. Now, another thing is that all molecules are attracted to one another by a combination of forces, and these attractive forces becomes significant at low temperature and high pressure, then where intermolecular distance are shorter. Now, attraction between molecules will reduce the number of collisions. Then the average distance between molecule decreases. So pressure exerted by the gas in the container will decrease, and hence the pressure will be very much less than we expect. So this paragraphs actually deals with the effect of temperature and pressure on the intermolecular forces. Now, let us say at high temperature, the molecules will have a sufficient kinetic energy to overcome intermolecular attractive forces. But whereas as temperature is lowered, what happens to kinetic energy? Naturally, it will decrease, and finally, a point is reached where molecules can no longer overcome intermolecular attractive forces, and the gas will start to liquefy. That is, gas will turn into a liquid. So these are actually small paragraphs dealing with the behavior of real gases at high temperature, high pressure, low temperature, low pressure, etc. That is how the intermolecular forces will look like. Then how the volume will look like, etc. So you can just go through these paragraphs, and if you want, you can just write down it as points, and you can learn. Okay, nothing more to explain. That is, all these are simple sentences which can read through and you will definitely understand its meaning. Hope it is clear. Now we will go to the next session, which is about the study of deviations from ideal gas behavior. Now we know Boyle's law is PV equal to constant at constant temperature. Hence, at constant temperature, the plot of PV versus P, which is shown here, will be a straight line in the case of an ideal gas, and it is parallel to x-axis. See this one, the straight line. However, real gases will not show this behavior. This figure is already shown in one or in some slides given above, right? So this ideal gas, it has got a making an intercept of 1 on PV axis, whereas all the other gas deviates from this straight line. That is, ideal real gases deviates from ideal gas behavior at high temperature and low pressure. That is, um, at this is the case of an ideal gas. This intercept, let it be 1, and all the other gas deviates from this ideal gas behavior at low temperature and high pressure. That is, an ideal gas behave like a real gas only at high temperature and low pressure. So remember that condition which is already mentioned above. So from these plots we observe that for gases like hydrogen, helium, etc., PV increases continuously with increase of pressure, right? It is very clear from here. Whereas for gases like carbon monoxide, CH4, etc., which is shown in this figure, PV, what happens to PV? It first decreases. That you can see a dip here. First it decreases and then it increases. Okay. It first decreases with increase of pressure and then reaches a minimum value, that is there is a dip there, and then it increases continuously with increase of pressure. See the figures for carbon monoxide and CH4. In the case of hydrogen and helium, PV is increasing with increase of pressure, whereas in case of carbon monoxide and methane, CH4, PV first decreases, reaches a minimum value, and then increases continuously with increase of pressure. Now, so all these graphs you can study. So see, this is the best way to draw the graph. They have marked only the y-axis, x-axis. They have marked ideal gas behavior and all. So this is the correct figure. So you can study this figure. It actually well explains the behavior or the deviation of real gas from ideal gas behavior. Similarly, if we plot experimental values of pressure versus volume at constant temperature and theoretically calculated values from Boyle's law, the two curves do not coincide. It is also clear no curve is coinciding, they are all independent of each other. Okay. From above graphs, we observe that at high pressure, a volume which is observed is higher than that of calculated volume, whereas at low pressure, the observed and calculated volumes approach each other. So that is the relation between between pressure and volume. That is, at high pressure, volume is higher than the calculated volume, whereas at low pressure, both observed and calculated volume, both of them are equal. That is, they approach each other. Now, real gas deviates from ideal gas behavior, and that deviation can be studied using a particular quantity Z, which is known as compressibility factor. It is defined as V real by V ideal. That is, volume occupied by real gas by volume occupied by ideal gas. For an ideal gas, PV equal to nRT, that we know. So compressibility factor Z is equal to 1. Whereas for real gas, they do not obey ideal gas equation, that is PV not equal to nRT. Therefore, compressibility factor Z is not equal to 1. Hence, two cases arises, that is when Z is less than 1. For example, for CH4 and carbon dioxide, etc., the gas show negative deviation. That means the gas show more compression. Why? Because attractive forces dominates among the molecules of these gases. Now what about Z greater than 1? In such cases, gas show positive deviation. here it was here it was negative deviation, here positive deviation. So in the above case, gas shows more compression, but in this case gas shows less compression. And which force is predominant there? Attractive force. Here which force is predominant in this condition? Repulsive forces. Greater the departure in the value of z from unity, greater will be the deviation from ideal behavior. So uh, we have a compressibility factor value z. Suppose that it has a value something like 1 or like that. Now greater the deviation from this behavior, greater will be the deviation from ideal gas behavior. So this can be clear from this graph, that is ideal gas, this one is having exactly the value 1, which is having the more deviation, maybe ch4, it is highly deviating from this value of 1. Okay, so greater the deviation from z equal to 1, greater will be the deviation from ideal gas behavior. Now as temperature and pressure, at the same temperature and pressure, the extent of deviation mainly depend upon nature of gas, which is shown in this figure. At intermediate pressure, that is at pressure not too high and not too low, carbon dioxide shows much larger deviation, that is negative deviation, when compared with hydrogen and nitrogen. Okay, yes, this is clear. This is having, this one is line for carbon dioxide, it is highly deviating, that is it first decreases, reaches a minimum value and then increases. So it is highly deviating from this ideal gas behavior, the value of 1, right, when compared with all the other gases. That is what written above. Now for same gas at a particular pressure, the extent of deviation depends upon pressure, depends upon temperature. This is for nitrogen gas. PV by RT is drawn for various values of P for different temperatures. So from this figure is once again drawn. It is already explained, but let us see it once again. As temperature increases, minimum in the curve shifts upwards. Ultimately, a temperature is reached at which Z is close to 1 over an appreciable range of pressure. Uh, for example, in case of nitrogen at 323 Kelvin, the value of Z remains close to 1 up to nearly 100 atmospheres. So, this is the ideal gas behavior at 1. And after that, let us see all the gases, the gas for, that is here it is shown only for nitrogen gas. It is deviating at various temperatures. 3 temperatures are shown here: 200 Kelvin, 500 Kelvin and 1000 Kelvin. At 1000 Kelvin, PV by RT increases with the increase in P. There is a continuous increase, you can see. But when temperature becomes 500 K, what happens? PV by RT, first of all it decreases to a minimum and then increases. Then what happens when the temperature is still lowered, when it becomes 200 Kelvin, PV by RT, it decreases to a minimum value, that is there is a more dip there and then increases continuously. So as temperature is decreased, the dip actually increases. That is this one is a straight line. There is a small dip for 500K and there is a large dip for 200 Kelvin. So the dip actually shift upwards. You can tell in that way also. The dip shift upwards or the dip decreases with increase in temperature. Okay, that is what written here. Minimum, that is the dip in the curve, shift upwards as temperature increases. Now, the temperature at which real gas behave like an ideal gas over an appreciable pressure range is called boil temperature or boil point. That's a definition you have to study. And from this plots 3 and 4, you can see that at ordinary pressure, Z is close to 1. That is, deviation from ideal gas behavior is small. That is, we can apply ideal gas law. Now, let us see the significance of this compressibility factor Z. Z can be written as PV real by nRT. If the gas shows ideal behavior, then PV real by nRT, that is, from that V ideal will be equal to nRT by P, that is equation 2. Substituting this value of nRT by P in equation 1, what we get is Z equal to V real by V ideal, which is already told. So compressibility factor is defined as ratio of actual molar volume of gas to calculated molar volume. So this definition is important that you have to study. Now the causes of deviation from ideal gas behavior. As stated above, real gas or ideal gas equation PV equal to nRT only if pressure is low and temperature is high. This condition is every time it is repeated, that is a real gas behave like an ideal gas only at high temperature and low pressure. However, if pressure is high or temperature is low, then what happens? Real gas deviates from ideal behavior. Now the reasons for such deviation or the reasons for such a behavior shown by real gases is mainly due to the following two assumptions. Which are the assumptions? When compared to total volume of gas, volume occupied by gas molecule is negligible. That is the first assumption. The second assumption is that the attractive force or repulsive force between gas molecules is negligible. Now the first assumption is valid only at low pressure and high temperature. When volume occupied by gas molecule is negligible compared to volume of gas. Okay, but at low temperature or at high pressure, molecule become incompressible. As a result, what happens is that volume of molecules cannot be neglected when compared with total volume of gas. Now the second assumption is not valid when pressure is high and temperature is low, but at high pressure or low temperature, volume of gas is small. As a result, what happens? Force of attraction becomes appreciable and it cannot be ignored. So this session is also important, that is, what are the causes of deviation from ideal gas behavior, these two slides. Okay, so just read through it. If you want, you can make a note of yourself by connecting the points discussed here. Okay, so today this is enough. Thank you.